This is chapter 19 video reassessment. I'm doing problem number 85 from the textbook, and it's a problem dealing with the magnetic force that is generated between two wires here and here that are suspended by some strings by the whatever kind of metal pole, whatever you want that to be. And we're seeing if we can get these two, well, we're trying to measure the distance between the two wires whenever the current is turned on. So whenever we turn on the force, whenever we pass the current through the two wires, they need to be moving in, the current needs to be moving in opposite directions for them to actually repel each other, one going clockwise and one going counterclockwise. But in order to figure out the distance between those two, we need a little bit more than that because there's other forces at play. The main one really being the force of gravity, which is pulling those two strings, pulling on the strings, trying to move these two wires close together. So what we're given is we're given the length of all the strings. We are given the mass by distance of each of the wires, and then we are given the current that runs through the wires whenever we turn it on. So for this, we actually need something from 191, which is our tension, because the tension of the strings actually has a lot to do with, because there's tension made whenever gravity is pulling down on the string, so that has a lot to do with how close these wires can either get apart or actually get smushed together. So that will create a force, and then there's an angle right here, which we kind of have to approximate, but by the time it's said and done, we won't really need it, because all we really need is, the main thing that's really happening is the force of gravity, the length of the wires, the current, one of our constants, mu naught, and the mass by the distance. So pretty much, whenever we go through there, we start out by looking at our tension, and there's two tension equations here. We've got tension equals the force times sine of theta, but since we're not given theta, we kind of just approximate it, and I just kind of went with 45 degrees just to see what was going on. But that, well, whenever I started out, I did that, but whenever I actually looked at it again, and yes, I kind of had to use some online help because, yeah, this one was a doozy. So after that, I realized that it actually needed tension equals mass times gravity over the cosine theta. So, but whenever you put those two together, you get this little guy right here, which is actually mass times gravity times tangent of theta, and that gives you that force. So we pretty much canceled out the t's right there. But then we put that together with, right here is the force of the magnetic field due to a straight line. And then we combine that with this tension equation. I can't remember words. And that gives us this little guy, which gives us our R, which is our radius, but we kind of ignore that. It doesn't, we don't ignore it. It gets canceled out with some of the figuring. And then that pretty much just take that into this little equation here, plug in your numbers, and that gives you 4.9 centimeters. And that's the distance from here to here whenever the current is turned on. And in order for that distance to actually happen, these two wires have to create a magnetic field that is opposing each other, so that way they repel. So in other words, they're basically like two north poles running alongside each other, so they repel each other, and they won't really repel and hold. They'll kind of swing because that force of gravity is going to keep trying to pull them down. So that's pretty much the second part of this. The camera will focus. Why are you not focusing? Well, this part pretty much says the current running through the currents have to be running opposite directions. That's pretty much all it says right there. Sorry, you can't see it.